All right, welcome. Today we're diving into one of the absolute cornerstones of artificial intelligence, the A-star search algorithm. I know, sounds kind of technical, but this is the hidden genius behind so many things you use every single day. And we're going to figure out exactly how it finds the smartest, most efficient path from point A to point B.
So, have you ever really thought about that? You pull up your maps, you punch in a destination, and it just knows the best way to go. Or think about a video game, where an enemy character seems to have this uncanny ability to find the perfect route to you. Well, it's not magic, it's actually a really brilliant piece of logic. And A-star is one of the best in the business at doing just that. So here's our game plan. We're going to break this down into 5 simple steps. First, we'll see what makes A-star so smart. Then we'll uncover its secret formula. After that, and this is the fun part, we're going to put it to work with a real example. Then we'll see it find the perfect path, and finally, understand why it's such a superstar in the world of algorithms. Okay, let's jump right in. To really get why A-stars is so cool, you first have to understand that there are basically 2 ways to search for something. You can either do it blindly, or you can do it with a little bit of inside info.
So on one side, you've got what we call uninformed or blind searches. Seriously, just picture yourself wandering through a giant maze with no map, just trying every single path until, oopsie, you finally stumble upon the exit. It works, but it's slow. On the other side, you've got informed searches, like A-star. This is like having a magical compass that always points kind of towards the exit. It uses extra knowledge, a little cheat sheet we call a heuristic, to make these really smart guesses and avoid wasting tons of time on routes that are obviously going nowhere.
So what's the secret sauce behind all these smart decisions? Well, believe it or not, it all boils down to one elegant and really simple formula.
And here it is. This little equation is the engine that makes A-star run. Don't let the letters scare you, it's super intuitive. F of n is just the total estimated cost of any path, and we get that number by adding 2 other values together, g of n and h of n. Let's break down what those actually mean.
Think about it like you're on a road trip. G of n is the actual distance you've already driven. It's a fact. You can look at your odometer, you know exactly how far you've come. H of n, on the other hand, is your best guess of how much farther you have to go. It's like the as the crow flies distance on a map, a straight line to your destination. It's not the real road distance, but it's a pretty smart estimate, right? A-star is so brilliant because it's constantly balancing these 2 things, what it knows for sure about the past and its best guess about the future.
And that brings us to the name. You know, the star and asterisk? It's not just there to look cool. It means the algorithm is admissible, and that's a technical term with a really powerful promise. A-star is guaranteed, absolutely guaranteed, to find the best possible solution. It won't just find a path, it will always find the shortest path.
Okay, enough with the theory. It's time to put A-star to work. Let's actually walk through an example step by step and watch how it thinks. All right, so here we are at our starting point, node S. Now the cost to get from S to itself, our g of n, is, well, 0. We haven't gone anywhere yet. The heuristic value, h of n, is given to us on the node. It's 14. So the total cost, f of n, of just sitting at the start is 14. Now, where do we go next?
Okay, here's our map. We need to get from S all the way over to G. From our starting point S, we have 2 choices. We can go to node B or we can go to node C. Let's calculate the total cost for each option. For the path to B, the actual travel cost is 4, and B's estimated cost to the goal is 12. Add them up, and you get a total of 16. For the path to C, the travel cost is 3, and C's estimated cost is 11, which gives us a total of 14.
So what does the algorithm do? It's simple. It always chooses the path with the lowest total estimated cost. Since 14 is lower than 16, A-star says, okay, I'm going to check out the path through node C first. It doesn't forget about B, though. It keeps that path to B in its back pocket, just in case. But for now, we're headed to C.
All right, we've arrived at C. Now we have 2 new options, go to D or go to E. Let's run the numbers again. For the path down to D, our total travel cost so far, the g of n, is 3 plus 7, which is 10. We add D's heuristic of 6, and we get a total f of n of 16. For the path over to E, the travel cost is 3 plus 10, so 13. We add E's heuristic of 4, and we get a total of 17.
And whoa, hold on a second. This is where you see the real genius of A-star. Our new best path, the one going through C to D, has a cost of 16. But wait a minute, remember that other path we put on hold? The direct shot from S to B? That also had a cost of 16.
we have a tie. So what does the algorithm do now? It has to consider both possibilities.
So the algorithm says, okay, let me just check out that other promising path from S to B. From B, we could go to F or to E. But when we calculate those paths, we find out that both of them, S to B to F and S to B to E, results in a total estimated cost of 20.
Now, since 20 is way higher than the 16 we have for our other option, the algorithm intelligently says, nope, that's a dead end. That route through B looked promising for a second, but it turned out to be way more expensive. So we go right back to our best option and keep exploring from node D.
Okay, back on track. From node D, our only choice is to go to E. The total actual cost to get there is now 3 plus 7 plus 2, which is 12. We add E's heuristic of 4, and our total cost is still a very promising 16. And finally, from E, we can get to our goal G. The actual cost is now 12 plus 5, which is 17. And what's the heuristic of the goal? It's always 0, of course, because we're already there. So our final cost is 17.
And just like that, we've reached the goal. The algorithm checked out the best routes, it backtracked when it hit a dead end, and now it has found a complete path from start to finish.
So what's the final answer? It's 17. And because we know A star is admissible, we know this isn't just an answer, it is the best answer. The absolute lowest cost to get from S to G is 17.
And this is the exact route it found. By constantly and cleverly balancing the cost of the path that's already traveled with a smart guess about the path remaining, A star navigated this whole graph and found the single best solution, S to C, to D, to E, and finally to G.
Okay, so let's zoom out for a second and just recap what makes this algorithm so incredibly special and why it's used all over the place.
It really comes down to 3 key things. First, it's an informed search. It's not just wandering around blindly. Second, it's admissible, which is our rock-solid guarantee that it'll find the best possible path every single time. And third, it finds that optimal path by doing that beautiful balancing act between the actual cost it's already paid and the estimated cost to get to the finish line.
Now, A star is amazing, but it's not a silver bullet. It has one major weakness. It has to remember all of the different paths it's considering. So on really, really big maps where there are tons of choices at every single turn, the amount of memory and time it needs can just explode exponentially. For really complex problems, this can be a serious bottleneck.
And that leaves us with one final and really crucial question. The entire performance of A star, how fast it is, how efficient it is, it all comes down to that one little number, H of n, the heuristic. Its quality basically determines everything. So what makes a good estimate? And what happens if you're a little bit off? What if you overestimate or underestimate the path to the goal? Well, that is a very deep topic and one for another day.